and for the invitation. So I'm happy to tell a bit about some recent work we finished with Michel Luken and Ashwin Vishwanath. So clearly I'm going to be talking, let me also just say in the beginning, if there's any questions, please feel free to interrupt me. I roughly prepared something for 40 minutes, but I'm happy to cut down on that and have discussions instead, in addition to the 5-minute questions. So, right, so clearly I'll be talking about topological order. So I thought it'd be fun to kind of set the stage with a brief, very brief historical overview of this concept. Right, so if we go back almost 50 years ago, Anderson kind of came up with the first instance of what we now think of as a topologically ordered phase of matter. So inspired by Pauling, he came up with this concept of resonating valence bond states. For example, if you have a spin-a-half magnet, if the singlets are not localized to a particular region in space, but instead are fluctuating all over, such as here, a quantum superposition of many different singlet coverings, then Anderson realized that this state would form a new kind of insulator that would not be characterized in terms of symmetry breaking and had some exotic properties. And so that was the first kind of theoretical example of topological order as we now understand it. And kind of separate from that, there was a sudden discovery in the 80s of the first experimental example of topological order, right, with the discovery of the fractional quantum Hall effect. Right? So now we know and appreciate that those different plateaus are actually topologically ordered insulators with fractional quasi-particles and these kind of exotic properties. And that discovery also, of course, gave a big boom for the community to investigate what kind of exotic phases do there exist. And this partly also culminated in the 90s with the first kind of real formalization of what we now mean by topological order. In particular, it was realized that there was this kind of possibility of the low energy effective theory could be a so-called topological quantum field theory. And we got this notion of topological order, where then the ground states, say, would have robust degeneracies, fractionalized quasi-particles, and lots of very interesting properties. This was by no means the end of that. Actually, it was in a way the beginning of the real theoretical exploration of what kind of topological phase of matter there exists. And so there's been a lot of interesting work over the decades. And so one can then ask, okay, where are we now, right? And so here, I can quote an eminent physicist, right, expert in these matters. And so this is from his webpage. So I actually don't know exactly what year it's from, but based on the references and citations and the rest of the text, it was roughly around 2010. So where Matthew Fisher says, unfortunately, we have yet to unambiguously identify any topologically ordered phases in any real material outside of the quantum Hall effect. Here referring, of course, to the fractional quantum Hall effect we just saw. He continues, this is a dire situation and frankly is egg on the face for the theoretical community. So while this was written about a decade ago, I still think the evaluation applies at the moment. Of course, this is not to say that there are not promising ventures, and also on the same webpage, of course, Matthew Fisher goes on to explain that there are many promising directions, and there's also still the case today, right? Of course, frustrated magnets are very promising candidates for realizing spin liquids. Also, the recent developments in twisted graphene layers, and there's many other that I'm not listing here. So there's definitely not a shortage of interesting directions to explore, but I do think it's fair to say that the fractional quantum Hall effect is the only really uncontroversial citing of topological order to date, where one doesn't have to, kind of squint the eyes, and one can just really be confident that there's topological order. And this is also partly the motivation of our work and the context of the talk today, where we'll be trying to, today I'll be telling you about a model that will actually be realizable with current methods, and it would realize a topological order that is distinct from the fractional quantum Hall states. And in particular, we'll focus on the simplest possible, at least theoretically, from a theoretical perspective, the simplest possible topological order, which is called Z2 topological order. So there's many different ways of characterizing it. Kind of the one sentence way of summarizing it, which is maybe not the most intuitive for everyone, is the deconfined phase of the Z2 gauge theory. Okay, but let me kind of flesh this out a bit more. So actually, it's naturally a part of Anderson's original concept of resonating valence bond states. It's kind of, in a sense, an example of that notion. And since that had also been Anderson's original work was a seminal paper, but not all the key aspects were realized back then. In particular, especially in the 90s, it was realized that like a good place to look for these kind of Z2 topological ordered phases is in frustrated magnets, which moreover are non-bipartite lattices. The non-biparteness is related to the Z2, but let me not get distracted by that now. And a real important contribution came in the 90s with Kitaev kind of finding, for the first time, as far as I'm aware, an exactly solvable model that realizes Z2 topological ordered phase, right? Which you all know now as a Toric code model. And he didn't just introduce a solvable model, but he also kind of emphasized what one can do with it, and that it can be used to actually do fault-tolerant quantum computation using topological qubits. So it was super exciting work. Separate line of work that was also very important, at least for the talk that I'll be for the talk today, is the realization in the early 2000s that also dimer models on non-bipartite lattices, such as a triangular and Kagome lattice, can naturally give rise to a Z2 spin liquid in certain regions of the phase diagram. As a side comment, I will use the word Z2 spin liquid, Z2 topological order interchangeably, right? And so, and this is by no means all the work that's been done on Z2 topological order, but these are some kind of key bits that I want to highlight. And so there's not a shortage of nice models that realize topological order, but none of them, so thus far, maybe one day, but thus far, none of them has been realized in the lab. And so in this talk, I'll be trying to show you that Rydberg atoms actually offer an ideal platform for realizing Z2 topological order. And perhaps one day also other types of topological order, but that's we haven't figured out just yet. Good. So now is a good point to maybe explain what I mean by these Rydberg atom setups. So what they would do in the lab is they take an atom. The precise details of the atom is actually not that important. In practice, it might be a rubidium atom, and they hold it in place using optical tweezers. That's what the red kind of signifies here. And so we can make one-dimensional, two-dimensional, one day also three-dimensional arrays of these Rydberg atoms. And the key bit is that each atom is an effective two-level system. So either it's in its ground state, as depicted here, or using a very particular laser frequency, it can be excited to a highly excited Rydberg state. So that's noted here. And those are, to good approximation, the only two states one has to think about. And so that's the setup for a single kind of Rydberg qubit, if you wish. But there's also an interaction, which is of the type that if two nearby atoms are both excited, then they will feel a certain energetic penalty. Okay, so let's put that in some, let's quantify that a bit, and I want to give you the Hamiltonian. So here's the Hamiltonian for Rydberg atom array. So the first term is some kind of Rabi oscillation induced by a laser. And actually, by the detuning of the laser, you also get the second diagonal term, which will bias towards being in the ground state or in the excited state. Here I'm using a spin and a half notation, where, for example, spin down is the atom in its ground state and spin up is the atom in the excited Rydberg state. And as I mentioned, there's also an interaction, which is only non-zero if both atoms are in their excited state. So you get this density-density interaction. And it's understood that this is a type of van der Waals interaction, which in this case is a 1/R36 decaying potential. So naturally, that comes with a length scale, R subscript B, which is referred to as the Blockade radius. The reason for this is that if one considers two atoms within this Blockade radius, then this potential is huge. And that basically prevents double occupancy within this Blockade radius. This is a cartoon picture here. So let these black atoms denote where our atoms live. And let's suppose we tune the Blockade radius to be roughly two lattice spacings. Then if this central atom is excited, then this potential essentially prevents any other atom in this disk from also being excited. This notion was kind of pointed out and discovered in the early 2000s, and it's referred to as the Rydberg blockade mechanism. And this will be the key mechanism that we will use to realize the Z2 spin liquid. Okay, so that's kind of the key player, this kind of Rydberg atom array. Oh, sorry, maybe I forgot one thing I want to mention here is that the original potential is 1/R⁶, but to a good approximation, we can actually approximate it by a step function. It's because 1/R⁶ is such a steeply decaying function that you see outside the blockade radius, it's approximately 0, of course, with some error, and inside the blockade radius, it's effectively infinite. At least it's a good kind of approximate model to study. In the end, of course, one wants to confirm that the salient features survive to the full 1/6 potential. But it's very useful to consider this more simplified model, in which case this becomes the Hamiltonian, where the Hamiltonian looks like a single side Hamiltonian. So we have this single spin flip operator, but now it's multiplied with a projector P. And all this projector P does is it ensures that because of this infinite potential inside the blockade radius, it ensures that there's no double occupancy within the blockade radius. Okay, and so this is called, for natural reasons, it's sometimes referred to as the PXP model. And in particular, it was quite prominent in some recent literature on 1D quantum scar states, which were discovered actually in these Rydberg setups. But I don't really want to discuss about that. For those of you who are familiar with the work on PXP model, you can kind of interpret our work as kind of a 2D generalization of the PXP model, where it apparently gives rise to a Z2 spin liquid. Okay, so brings me to the outline for the next roughly half hour or so of the talk. And we'll be considering Rydberg atoms that are positioned on the links of the Kagome lattice. And we will see that using this blockade mechanism, that actually naturally gives rise to a dimer model, and actually relatedly lattice gauge theory. And then we will numerically confirm that this indeed is actually in the deconfined spin liquid phase. This will be the majority of this talk. And then towards the end, I'll briefly show that this can actually be experimentally realized, and also give some first steps towards actually, discussing the practical uses this can have for constructing topological qubits. Maybe this is a good moment to already just pause and see if there are any questions at this stage. Okay, if not, let's jump in. Good, so let's consider the model. I already told you the Hamiltonian, it's this PXP type Hamiltonian, but you have yet to specify the lattice where the atoms live. So I already mentioned they're on the links of the Kagome lattice. So this is what I'm drawing for you here. So each black dot is where an actual physical Rydberg atom would be living, which can be in a ground state or excited state. And then we can also tune our blockade radius in experiment. And we choose it to be as large so that this red disk becomes the blockaded disk, meaning no two atoms can both be excited within this disk. Okay, that's what this P does. It projects out double occupancy. Okay, so now we've defined our model. Now you might ask, why this model? Why this choice of lattice? Why this choice of blockade radius? Well, okay, let's explain that now. So the blockade radius, you see, is such that if the central atom here is occupied, none of the nearby 6 bonds can be occupied. Right? So what kind of possible states are there? Like, let's consider an atom that's excited here on this bond. So that's kind of a spin up effectively. So none of those nearby bonds can be excited, but for example, this one can. That's fine. And so one can keep kind of filling in. And this is the state I've drawn here on the bottom left is a state that's consistent with this blockade condition. But to appreciate its significance, it's useful to actually just replace circles by ellipses. So they look like dimers. And then you see that this constraint that we just talked about is effectively telling us that no two dimers are allowed to touch, right? This is exactly a dimer constraint. So we see that with this blockade in this lattice, we effectively get a dimer state on the Kagome lattice with one caveat, right? So the blockade tells us dimers cannot touch, but it doesn't a priori ensure that we have a maximal filling of dimer coverings, right? And a conventional dimer state, you actually want it to be complete covering of the lattice. So generically in this model, we actually have dimer coverings with monomers. So monomers are names for if you have a certain vertex where no dimer is touching, you say this is a monomer. It's kind of like a doped dimer model. Right. And of course, as one tunes delta, as delta becomes larger and larger, one can get arbitrarily close to maximal filling. Okay, that's one thing to keep in mind. But okay, so that's good. So we have an approximate dimer model in the Kagome lattice. Now why is that of interest? What's the link with the Z2 spin liquid? Well, to appreciate the link, I want to have one slide take one slide to explain the connection between dimer models and Z2 gauge theory. So for the moment, let's think of conventional dimer models where there's no monomers. Okay, so it's complete coverings with using dimers of, say, of the Kagome lattice. Now, basically, such dimer models are equivalent to pure gauge theories. And to make this connection, basically, that's what this one sentence here tells us. Any dimer configuration you draw on the Kagome lattice, it basically encodes an electric field where the presence or absence of a dimer is basically telling you whether the electric field is 1 or 0, just like a two possible values for your electric field. The reason this is a meaningful kind of reinterpretation is because of the dimer constraint, right? So in a dimer model, we're ensured that every vertex has exactly one dimer touching, so on this blue dashed line. Now, that basically is equivalent then to a Gauss law for your electric field, that the divergence of the electric field is 1. If this were 0, we would call it a pure gauge theory with no matter. The fact that it's 1 rather than 0 is as if you have a classical charge that lives at every vertex of your Kagome lattice. But we still call it a pure gauge theory because that matter is completely classical. There's no dynamical matter. This 1 is like a classical number. For that same reason, it's sometimes called a odd Z2 gauge theory. But anyway, it's a pure gauge theory. You only have your gauge degree of freedom as your dynamic variable. But you can still consider monomers. So if you, for example, remove one dimer, that basically creates 2 monomers. But in a dimer model, those are not dynamical. So those are like kind of classical test charges. And you can put them at different distances from one another. And then you can ask, are those monomers confined or not? Basically, is there finite or infinite energy penalty for separating them arbitrarily far away, these kind of test charges? And depending on the answer of that question, you get the 2 possible phases of a pure gauge theory. So either you find there's a confining energy cost, which is the confined phase, or you find that they're deconfined. And as a side comment, it's known for these non-bipartite lattices, there's a certain Lipschutz-Mathes type theorem, which says that if you're in the confined phase, you actually have to spontaneously break some crystalline symmetries. So just keep that in mind. And the other option is in the deconfined phase, as I said. And this is basically what we know as Z2 topological order. Okay. Where, for example, the monomers would be the E anyons that you might know from the Toric code model. And this is in the phase we want to realize. We want to have some kind of deconfined phase in this approximate dimer model. But for that, we need strong dimer resonances. The reason for this is the following. If you have very few dimer resonances, then your state prefers to have some classical-like dimers. And then you can kind of convince yourself that if you try to separate 2 monomers far away from each other, you'll end up changing the position of an extensive amount of classical-like dimers, which will give you an extensive energy cost, and will then mean that those 2 monomers are actually energetically confined, which is the definition of the confined phase. So we actually need strong dimer resonances to kind of get a quantum soup of fluctuating dimers, and that will then realize a Z2 spin liquid. So that's what we're after, okay? And it's kind of encouraging to know that there are known models of dimer models in the Kagome lattice which realize a Z2 spin liquid. However, the kind of known exactly solved model, the Hamiltonian is quite unrealistic, sadly. So there's 32 types of resonances. The smallest one involving 6 dimers, the largest probably 12. So we cannot just try to realize that model. And this is a bit a downside of dimer models in general, that the benefit is they hardwire, they give you a gauge theory by construction. So that's a good place to look for a spin liquid. The downside is that the off-diagonal moves are quite non-local, right? You need many dimers participating at the same time, which can be hard to construct this kind of kinetic term. So here we're actually saved by a property of our model, right? To remind you, we didn't have a pure dimer model. We had dimers with dynamical monomers. And this actually helps us, right? Because if you have monomers, it's possible to have single-site kinetic terms. Indeed, that's what our PXP does, right? So if you have a dimer covering, you're always allowed just to remove a dimer, right? Which creates 2 monomers. And if one actually starts in the large delta regime, where one a priori has a degenerate manifold of fully packed dimer coverings, one can then expect that perturbatively, using these kind of single-site kinetic terms, you can generate these dimer resonances in perturbation theory. right? And for example, at leading order perturbation theory, get a certain hexagon resonance, for instance. So there's the hope that even though our Hamiltonian only has a single site kinetic term, that in a certain regime of our model, we hope that it induces dimer resonances, which are then naturally going to give rise to a Z2 spin liquid. So that's a main advantage of actually having dynamical monomers. A second kind of cute advantage, or as the cute fact, is that since we now also have dynamical monomers, we can also basically create a third phase of a Z2 gauge theory, right? So already we had confined and deconfined as two possible phases of a pure gauge theory, but once you introduce matter, we know you can also drive it to a Higgs phase. And in this case, this would correspond to condensing single monomers. Right, and unlike the confining phase, this would not be accompanied with crystalline symmetry breaking. So if you then are really able to have both the Higgs phase and the deconfined phase, you would see two completely featureless phases, which are still separated by a thermodynamic phase transition. Good. So that kind of was the definition of our model and giving the theoretical justification for why we're looking at that model in the first place, kind of the motivation. And that's as much as we can do analytically. Okay, so the model itself is not solvable, so we have to turn to numerics now to figure out, does it really end up realizing a Z2 spin liquid? Okay, so for convenience, I put our blockade model here again, the PXP term. And here again, here's the lattice, links in the Kagome lattice with this particular blockade radius. And now we just simulate this model. The tool we're using is the density matrix normalization group. It's in principle a one-dimensional method, but by putting the system on a cylinder with varying circumferences, one can actually simulate this. Good. And so here I'm showing you the resulting phase diagram for a particular size of the cylinder. So to give you a sense of the cylinder, this is the circumference. So this is a periodic direction, and it's say infinite in the horizontal direction. So we're doing infinite DMRG. So what do we find? Well, if delta is very small, okay, well, by already looking at the Hamiltonian, you see if you make delta even negative, you see that you can get arbitrarily close to an empty state. So that will surely be a product phase for small enough delta. Whereas if delta goes arbitrarily high towards infinity, we already discussed that we get arbitrarily close to a pure dimer model, where there's only two possible options. Either we get a confining phase, which due to Lipschitz lattice will actually look like a valence bond solid, or we get a deconfined phase. A priori, we didn't know what we would get. And then we were a bit disappointed when I did the numerics and we found, oh, actually it's a valence bond solid. We get a confining phase for large delta. As the interesting thing is that as the unit cell is quite non-trivial, and it relates to previous studies of spin liquids or phases proximate to spin liquids, but it's more a side note. Although we were kind of demotivated in the beginning, to our amusement, we found that actually as you tune delta, in between, we found a third phase, which is featureless. So here I'm showing the density plot of dimers. There's no obvious symmetry breaking, but yet it's separated from the trivial product state phase by a thermodynamic phase transition. For example, this red line here is the Xi, so that you see the correlation length diverges. And we're always characterized by some large entanglement plateau. So that's already encouraging. So maybe this is our Z2 spin liquid, consistent with the fact that we know Z2 gauge theory has three possible phases. Okay, so as a first kind of sanity check, right? If we want to claim this is a spin liquid, due to this regime still being close enough to an effective dimer model, well, then one sanity check would be to look at the density, right? Because if we expect that this is still close enough to a dimer model, we expect the density to be quite close to a packed dimer configuration. So that's easy enough to calculate. So I want to draw your eyes to the red curve here. So I'm plotting the density. And we see that if delta goes to infinity, we get arbitrarily close to a quarter. That's the theoretical expectation of the filling factor for a dimer state. And we see it does decrease, of course, as you lower delta because of quantum fluctuations, right? These dynamical monomers. But still, it's relatively high in this intermediate regime. And it's only once we go through phase transition into the genuinely trivial phase that it plummets. So that's already maybe a first intuitive indication. But it's just that, it's just intuitive. That so far that's never going to count as any real evidence. So, okay, let's go to how do we actually confirm that this intermediate phase is a Z2 spin liquid. So for that, there's a variety of probes one can look at. right? So one can try to extract the topological entanglement entropy, which is predicted to be log 2. Or if the state is on a manifold with a non-trivial genus, such as the cylinder, one expects a ground state degeneracy. Relatedly, one can try to extract some certain universal information from modular transformations. And lastly, one can also try to characterize topological string operators and diagnose the phase and its nearby phase diagram in terms of those. So we did all of those things and all worked out perfectly. And with time considerations in mind, I don't want to discuss everything, so I'll pick out. I'll have one slide on the topological entanglement entropy, just because it's perhaps kind of the most standard thing to do, right? And it requires the least structure, right? One just calculates it and sees what the value it is. And then I want to focus on topological string operators, because they're kind of cool objects, but also very practically useful for both for diagnosing a spin liquid experiment and also eventually kind of thinking ahead of using this phase of matter to construct topological qubits. Such string operators would be basically essential. All right. Maybe again, it's a good point to just pause and see if there are any questions thus far before I continue with these 2 points.
Yeah, Ruben, maybe I can ask a question.
Please, go ahead.
So in this construction, you want to construct the Toric code between topological order. Is it easy to generalize to the double semming?
Yeah, that's a great question. Yeah, and the short answer is I don't know. Yeah, I don't know. But I agree that's kind of the natural next step to think about. You would want. Yeah, it's not clear to me because you would, at least the usual Toric code, you end up using some kind of phase factors in the Hamiltonian. And I'm not sure how you would introduce it here in the Rydberg Hamiltonian. But okay, it's definitely worth thinking about more. I don't know.
Okay. Okay.
Can I ask a question, please?
Yeah. Hey, Tor.
Actually, on the previous slide, the previous slide?
Yeah.
Is that the VBS order parameter? Sorry, no, that's not.
Yeah, right. So here it's good.
I max minus. Okay. Sorry.
Yeah. So I'm taking. So say here, right? I take the maximal, which is roughly 1,
right. No,
and the minimal.
And
you can do that also here.
I see. I was wondering, is the phase transition second order VBS to spin liquid?
No, it's first order. It's first order.
Okay.
I also see it in the energy. There seems to be a kink, but it's a very weak first order. I don't think it's necessarily weak. Well, it depends a bit on what one looks at. It's not weak in this sense because this filling just jumps. It's weak in the energy, but that's probably because of this perturbation theory factor. Anyway, it's maybe more of a side comment. But yeah, the conclusion is trivial to spin liquid is second order and spin liquid VBS is first order.
Okay, thank you.
Thanks for the question.
Can I ask a question?
Yeah.
Yeah. So if you go back one slide, I guess you had where you had the ring exchange term there.
This one?
Yeah, this one. So, but there are also competing terms where a dimer can just hop around, right? If delta is not infinite.
Yeah, right. So what I'm doing here is, so in the infinite delta limit, we get a generate manifold, and then I'm writing down the perturbation theory Hamiltonian in that manifold. So in that manifold, I really only have complete coverings.
Right.
Right.
So this is the strongest term.
Yeah, this is the strongest term.
I guess as you. Right.
Well, as long as perturbation theory is valid, I can write down a state that only has packed dimer configurations. But I am not presuming that perturbation theory is valid. So like in our numerics, we don't use perturbation theory. It's just more like an intuitive.
I see. Okay.
Yeah. We haven't really explored this more. One could try to see how much one can do with perturbation theory, but we haven't really pushed it.
Okay, thank you.
Thanks. Okay, so let me briefly touch on the topological entanglement entropy. So in short, by considering the system on circumferences, some cylinders of different circumferences, one can always cut this cylinder in two, calculate the entanglement entropy between two halves. And then the prediction is that this should scale linearly with the circumference because you have a gap phase, but there can be a constant offset gamma. This is called the topological entanglement entropy. And one important caveat here is that it is by now appreciated that certain systems can give like a spurious value of gamma, but usually that is specific to making a very particular cut, and that if you do it for a different cut, you don't get that spurious value. So for that reason, we actually do two different circumferences, like two different ways of gluing the circumference together. And we extract gamma for both, and we find basically log 2 in both cases. So maybe I can draw your attention to this plot at the bottom here. So delta over omega 1.7, actually that's in the intermediate phase. And so we see that as we increase the circumferences, the entanglement P scales linearly, but as we extrapolate backwards, we find that the offset is roughly log 2, even for both types of wrapping the cylinder around. And here I'm also plotting it as a function of delta. And this is just for two different circumferences. So this is not yet in the thermodynamic limit, but still for these two circumferences, we already get a nice approximate log 2 plateau in this intermediate phase, consistent with what one would expect. But then, for example, in this plot, I went to bigger circumferences, and which moreover confirms that this log 2 is not just some accident. Okay, so let's turn to topological string operators, which I think are quite fun objects. So one way of thinking about these topological string operators is that they're natural objects if you think about Z2 gauge theory. So basically, there's the so-called Toft line operator, operator, which is the line integral of electric field around a line. And you have the dual variable, which is the Wilson line operator, where you have the line integral of the gauge field. Now we want to know what are those objects in our actual lattice model. Well, the electric field is very simple, right? I already discussed that any dimer configuration is literally encoding an electric field. So if you want to know what is the electric field along a line, well, it's literally the parity of dimers along that line. So for instance, with this example state, if we want to measure the Toft line operator along this line, it's actually -1 because we intersect exactly one dimer. As for convenience, here is a definition of this line operator on a single triangle, which is just measuring the parity of any dimer that it intersects. So we refer to this as the P string operator, P for parity. So that's the easy one. Then there's also the dual line operator. Now, one useful hint is that, well, since there's dual variables, it cannot be diagonal on a dimer basis. It has to shuffle dimers around, right? And actually, if you think about it, there's only one kind of consistent definition of, given a string that traces bonds of the Kagome lattice, there's only one kind of operation that for any closed loop of this type, it will map a valid dimer configuration to another valid dimer configuration, basically toggling dimers and with particular rules given by this. Okay. However, if you have an open string and you apply the same rules, you will still get a valid dimer configuration in the bulk of the string, but the endpoints now can actually create monomers, right? So you see that by applying these kind of local rules, this state is transformed to this state, where we now have a monomer here and a monomer over here. And to remind you, monomers are basically the electric charges of the Z2 gauge theory. So in other words, we see that the E anyons are actually created at the endpoints of this Q, what we call Q string operator. This is very analogous to, for those of you familiar with the Toric code model, it's familiar. It's analogous to what we know from that model. And similarly, the endpoints of the parity string operator will actually create M anyons. So actually, after applying this string operator, we'll create an M anyon on this plaquette and this plaquette. But you might wonder, why don't you see it? Right here, you just literally see a monomer. Well, here, just the subtlety is the fact that we're acting on a classical dimer state, and a classical dimer state is a condensation of M anyons. So you do create an M anyon, but because it's a condensation, you don't really see it. Right? It only becomes meaningful once you consider a quantum entangled state with many different dimer fluctuations. But right, so the upshot is we have our two topological string operators, which create M and E anyons at their endpoints. And now we can actually use it to diagnose our phase diagram. Okay, so how to do this? Well, we already discussed there's three possible phases in a Z2 gauge theory. There's a deconfined phase, there's a confined phase, which is a condensate of M anyons, and there's a Higgs phase, which is a condensate of E anyons. And since condensates, they can actually be measured using these string operators because they will give long range order in the corresponding strings, right? For example, if you have an E condensate, you expect that this Q string, where E anyons are created at the endpoints, will have long range order if you act on it in the ground state. So this is what we can do. We basically measure long range order in these string operators The only caveat is we have to properly normalize our string operator because we're not in a fixed point model. I don't really want to go into that here. There's this basically, if you have this string like this, you normalize it by the square root of the closed version of that same string. So this was figured out in the 80s by Brickman, Fröhlich, Friedenhagen, and Markku. For that reason, we refer to the string order parameter as the BFFM order parameter. Okay, so let's see what we get if we we get our numerical wave functions using DMRG, and I just calculate these string order parameters. For example, in the trivial phase, I find that if I calculate the string order parameter for this off-diagonal string, to remind you, this is the one that created E anyons, I find it actually has long-range order in the ground state. This is a non-zero value here. This confirms that the trivial phase really is the E condensate. It's the Higgs phase of our Z2 gauge theory. And we see that the same order parameter is 0 in the other two phases. As a side comment, you can also consider the parity string along the circumference of the cylinder. And if you have an E condensate, you expect this to be suppressed because it's kind of a dual string operator, whereas it can be non-zero in the other two phases. And that's what we indeed confirm here. You can kind of flip it around. We go to the VBS phase, and now we find that although Q doesn't have long-range order, the other string, which creates M anyons, has long-range order, confirming that the VBS really is a condensate of M anyons. And again, we find that it's 0 in the other two phases. So what does this tell us? Well, it tells us trivial is E condensate, VBS is M condensate, and the intermediate phase doesn't have a condensate of either particle. This is consistent with it being a Z2 spin liquid. Moreover, because we don't have a condensate of M and E anyons, we can have non-zero values for the topological string operators around the circumference. This itself is a useful probe for the topological ground state degeneracy. But given time constraints, I don't want to go into that here. So I'm just flashing around that we check that we get topological ground state degeneracy on the cylinder. We can use these string operators to actually distinguish them. And from those calculating overlaps for those different ground states, we can extract certain information from these kind of modular transformations. All right, so that was all focusing on this Blockade model, where we had this exact PXP Hamiltonian. And there, I would say we're very convinced we have a Z2 spin liquid, as in this is very straightforward, everything works out perfectly. So that's great news. And the last few minutes, I just want to touch on also realizing it in the lab, or at least, towards that, right? I'm not going to show you experimental data. It's more about kind of taking into account the fact that the model in the lab is not the pure PXP model. And lastly, I'll make some comments on how we can use this to create a topological qubit. Maybe I can pause here for further questions before continuing with that.
I have one question. Which is the minimal dimension of the lattice you expect you need to see the order?
By dimension, you mean like the site, like how many sites, for example?
Yes.
Yeah, it's a good question. So in the Blockade model, it can be very tiny, actually. Do I have a? I think I have a plot later on. I can show you. But okay, do I have some picture? Sorry, but it can be even like this size or smaller. Should be enough to see topological degeneracy. But this is for the PXP model. Maybe it's a bit trickier in the van der Waals model, but
thanks.
Yeah, okay. All right. So yeah, I don't have much time left, so let me just briefly touch on these issues, and then feel free to ask afterwards about any of these aspects in more detail. So I just want to have one slide where we deal with the fact that we don't have the PXP model in the experiment, right? We actually have the 1/6 model. We can also do numerics on that. There's a tricky aspect, of course, which is that 1/6 is, it never stops, right? And using DMRG, at least DMRG on a cylinder, there's not an obvious way of just including all these interactions. So that's going to be the constraint of this method. But we can include certain interaction distances. The downside is one might not know what happens for infinite interaction, infinite range. The upside is that this model actually has a bunch of parameters one can use. So there's already the detuning that we had in the PXP model, but now we have two other parameters. We have this Blockade radius that can be tuned as a continuous parameter. And also there's actually an extra parameter on the lattice which I haven't really talked about before. But so intuitively, we have the atoms living on the links of the Kagome lattice, but one can tune how far away are these triangles from one another. And for any choice of row, you can still get an effective dimer model. And so you can play around with this extra parameter, this aspect ratio of your lattice, to figure out what is optimal. So let me just quickly show you some some data we have, for example, for this lattice, and what these kind of interaction distances. And we again find that there's this phase transition between a two featureless phase of matter. And the second one has topological ground state degeneracy on the cylinder. And we again use the string operators to distinguish the phases, and kind of all works out very nicely. Okay, so Melly also briefly mentioned that, so I kind of hammered on the importance of these topological string operators, because they're also useful to diagnose the phase in experiment and to actually use them for your qubit. Now, how do we measure them in experiment? So actually the diagonal string operator P is very simple, because in the experiment, they can actually just take snapshots of the atoms and just read off the parity. So that's beautiful, that should be fine. The off-diagonal string operator a priori is quite a bit trickier, but fortunately, there exists a rotation that rotates one into the other. Okay, so it turns out if you take your PXP or PYP, which can be implemented in experiment, the only caveat is P has a different blockade radius. So one has to basically tune the blockade radius to be slightly smaller, and then time evolve with this Hamiltonian over a certain time window, T, given by this value. And then if one then measures a diagonal string, it's equivalent to measure the off-diagonal string of your original state. So this way, P and Q string operators should be measurable in experiment. So that kind of gives us the necessary tools to detect it in experiment, in principle at least. And then one last slide I want to show before opening up to more questions is how this could be used to create a topological qubit. So this in a way is kind of the first step in the direction. There's much more to be done on it. But already now we can kind of see that it should allow for a topological qubit. The main ingredients we identify here are the following two, is that once you have your system with a boundary, from universal argument, there's two possible boundary conditions called E and M condensed boundary, which corresponds to the fact that there's two nearby phases, right? You have the Higgs phase or the confined phase. And also in our model, we know how to achieve both boundary conditions. It turns out by just changing the detuning delta on the boundary links, you can drive a boundary phase transition between the two different boundary conditions. All right, so that's one tool in our toolbox. The second is we also know how to trap E-anyons, right? Because E-anyon was literally just a monomer. So you can basically take out a vertex of your lattice, find the ground state, and then using topological string operators, we can confirm that this traps an E-anyon. Now, how does this help us? Well, this allows you to construct and toggle topological qubits, right? So for example, two possible planar ways of getting qubits without creating tori is either one has a rectangular slab with alternating boundary conditions, like M and E condensed alternatingly. And from kind of standard arguments, it's known that this is twofold degenerate. And then one can, for example, use this E-anyon to toggle the logical state of your qubit. Alternatively, one can only use an M condensed boundary, but create a puncture in your system. And again, this has actually a topological degeneracy that can be toggled with the E-anyon. And of course, a qubit is only useful if you can read it. And here we can use our topological string operators properly normalized to give you certain logical readouts. Okay, good. So I think I'm used up all my time. So the summary is that we saw how Rydberg atoms on the links of the Kagome lattice can naturally approximate a doped dimer model, which we then numerically observed to realize a Z2 spin liquid. And we actually have a concrete handle on this phase of matter using string operators, which should also be useful for then creating topological qubits. So thanks for your time.
Yeah, thanks, Ruben, for the very nice talk. We have several minutes for questions.
Hi. Yes, I have questions. So yeah, thank you for the talk was excellent. There are two parts to my question. The first part is, it's basically just about these string operators. So when you say measuring, so the first part is when you say measuring, I'm not quite sure what you mean. So I imagine if you take a ground state, you apply string operator, you can't really tell where the string operator was applied. It should be kind of invisible. And so I think I'm misunderstanding something there. And then the second part is, how experimentally accessible do you expect a movement operator to, or a string operator to be? So if you apply a string operator, or can you apply a string operator using instrumentation?
Yeah. Okay. Just to make sure, the first question is that what do I mean when I numerically measure it in the wave function, or you mean in the experiment? The first part of the question.
You know, either.
Okay.
Yeah, measuring where the string operator.
Yeah. Good. So the way to think about these string operators is that they're really kind of operators on our Hilbert space, right? So here I'm defining, if I think of the Hilbert space as just being a collection of triangles, right, with possible dimer fillings, then here I'm essentially defining a matrix on that Hilbert space, right? And so this is also what I do numerically. This is literally defining a 4x4 matrix of these 4 states. Like every triangle, to good approximation, has those 4 possible states because of this blockade constraint. And so we have a 4x4 matrix that we, and then that we define. And so now I can literally just act with that 4x4 matrix on my quantum wave function, right? So DMRG gives me an actual wave function, and on every site I can act with this operator. And then I calculate the overlap with the original wave function, right? So that's what I'm doing numerically to get these plots, for example. So that hopefully answers the first part of the question. Then about experiment, there one doesn't apply the string operator. It's even simpler is that what they do in experiments, so they have this quantum wave function in principle, like they can get the ground state for certain values of parameters, and then they literally kind of flood it with light and they do a readout. So they see like, oh, this atom was excited, this atom was not excited, and this atom is excited. So they get like a beautiful 2D picture of, filled and empty, if you wish. Like they get basically a dimer snapshot. And now they have that, of course, that's only one branch of your wave function, right? So you can do that readout many times, right? They create the same state, read it out, create the same state, read it out. And then they just do statistics on that, and they just basically calculate the parity from that data. Does that answer your question?
Yeah, I guess I'm wondering about the ability to manipulate anyons. Can you, for instance,
okay. Yeah, okay. That's another thing, right? So here I was focusing on the readout. So this is a good point. I would not use these string operators for manipulation for the simple reason that they're not fixed point string operators. So I think it's better to trap anyons like this, and then dynamically. So how was the anyon trapped? Well, we basically, one way of thinking was we remove these links, right? Now, better way to think about it is we change the detuning on those links so that the atoms like to be empty there. If you think about it like that, you see that you can kind of have it. If you now imagine that detuning to be a dynamical function, such that I maybe increase the delta function, the detuning here, but decrease it here. And this way I can actually move the E anyon around. So I would not use the string operators to move them around. I would actually use traps.
Okay. All right. Yeah, that answers my question. Thank you very much.
Thank you.
Thanks. Leon had a question, I think.
Yeah, let's see. Thanks. Nice talk. It's fun to see some of this stuff. I had a question about it went a little bit fast. We were talking about the van der Waals interactions.
Yeah.
You see exactly what you were doing there. Were you just choosing different radii for the projection? Or are you actually putting in potentials that
Right. So the blockade radius is fixed to a particular value. So what I'm doing here, what I'm showing with these different disks is those are just showing the different distances we have in our potential, right? From this side to this side is the purple disk, from this side to this side is the orange disk, etc. And so here I'm just visually showing what interaction distances am I including. Basically, what I'm really saying is that outside this, pink disk, I am putting my potential to 0, because in DMRG I have to basically stop it at some point. And so
in this case, you're studying the model with a potential just truncated.
Yeah, exactly. It's just truncation of the potential,
not the projection. Okay.
Yeah, exactly.
Yeah. Okay. I guess that was my main question. I might have thought there'd be more effects of that, as you, at least in this perturbative limit, the diagonal terms probably split degeneracies.
Yeah, you're right. So I think that this is the trickiest part. Indeed, this is truncation. So I didn't really have time to talk about this, but there is a sensitivity there that, for example, we've definitely seen parts where for a certain truncation distance, I see a spin liquid. Upon including more, the spin liquid can be gone, but then including yet more, the spin liquid is back. So, and here's a bit of the issue of DMRG might not be the best method to figure out what is really the true behavior for the infinite potential. But there's definitely, as you're saying, this issue of the diagonal splitting. Yeah.
Can I ask one more question? I'm not so familiar with the Rydberg atoms, but in a lot of these quantum simulators, there's maybe limitations on the amount of time that you can kind of run the quantum simulator. Is there, is there some notion for how long it takes to kind of evolve the system to the ground state? How you would actually prepare
Exactly
in this regime? So
yeah.
Again, because these dimer models can have very slow dynamics somehow.
Yeah. Right. So there's definitely kind of a time window for, so the way these states are prepared is not, as you're guessing, it's not by cooling down, but it's by some kind of adiabatic preparation. So one starts, say, this model for delta very negative, so it's close to a product state where one initializes it, and then one adiabatically ramps up delta. And of course, there's already an issue because we're claiming there's a phase transition to the spin liquid, right? As there would be. So I guess I'm trying to find this. So one would find over here, one would try to tune over here. And then, so there's a certain time window there, and that should be gap dependent. So that would require kind of a further analysis to see, what is the speed in practice one would need and things like that. Yeah.
Okay, that's helpful. Thank you.
Yeah, Taran, please go ahead.
A very nice talk. Thank you. So I was wondering, so there is this regime of just in the pure Toric code, if you add both sigma x and sigma z terms, so and suppose you set both of them equal to each other, then there's this line which is seems like an interesting gapless line which extends from the corner.
Yes.
Did you explore that? That's one question. And is there experimentally, is that reachable based on the parameters you have?
Right. So it's a good question. I mean, so we're not literally realizing the Toric code model, so it's hard to say what is the analogous thing.
Right.
But it would involve kind of exploring the path that will connect trivial to VBS, right? Because that's kind of what the reason you're talking about is.
You're just trying to condense both of them at the same time. Yeah.
Right. So one thing is in this model, unlike the Toric code model, there's actually a hard distinction between the E and the M condensate. It has to do with the fact that the M anyons have some charge, some projective charge on their translation symmetry. So this is the reason that the M condensate actually spontaneously breaks crystalline symmetries.
Right.
So one would have to explicitly break those symmetries, and then one should be able to connect them. And we haven't really thought about that yet.
But even if you can't connect them, you can still ask what happens close to the point you're trying to connect.
That's true. Yeah, that's true. Right. Yeah, it would be fun to explore. Yeah.
And maybe one more question. Experimentally, is it? I mean, this model, for example, doesn't have sign problem. Is there any experimentally you can make more general models, which I don't know. Have you one? For example, in the Toric code, adding, for example, sigma y term, we don't know how to solve that, at least on a computer, but analog of those terms, I don't know. This is very.
Yeah.
And
so you're asking like how to modify the Rydberg. Sorry. Oh, sorry. We briefly overlapped.
I don't know. We can chat this later. It's not a very good question anyway. So.
No, okay. But so basically, it would require. Basically, you're saying, is there some way of modifying the Rydberg Hamiltonian to make it have a sign problem? Right. And generate. Yeah.
Probably they can, and smaller.
Yeah, I don't know actually. Sounds worth thinking about.
Due to the time limit, let's maybe take the last question from Dominic.
Hi, Ruben. Yeah, thanks for a nice talk. So you guys have like a lot of convincing evidence as a spin liquid, but if I was thinking about being devil's advocate, is there any chance like some other phases are coming together to spoof this evidence? Like you mentioned this spurious topological entanglement entropy, and you guys take some precautions, but like, you know, you can always just make the spoofing model a bit more complicated, like the two different directions you take. If they both have like some subsystem symmetry, you entanglement entropy, and then you also have some like long range string order, and you have some degeneracy. So like there has to be some sort of subsystem symmetry breaking as well. But is it like completely ruled out that you could have some combination of subsystem symmetry protection and symmetry breaking spoofing these characteristics? Because you have like a lot of different tests.
Right. Well, I guess the question then becomes, what would count as a definite ruling out of all? Is there a way of definitely ruling it out? Let's see, we have the topological ground state degeneracy. You're saying, so that could be some symmetry breaking that has no, but it would have, even though local order parameter would be completely missed, right? Like that would
I guess
not
like
naturally...
sorry.
No, go on. Sorry.
I guess doing things in this sort of quasi 1D way is how you can miss things. If you know that all these operators are fully flexible and stuff, at that point it's really confirmed. It's like not some kind of spoofing. So, but maybe in the numerics, like often you will, because you're doing the quasi 1D thing, you'll look at like very straight lines and things wrapping around the cylinder exactly. Right. And that could be how you could miss it. But maybe you, I don't know, have you looked like sort of at deforming these operators just a little bit to see if they're sort of topological?
Yeah. Yeah, it was hard to say, because if we're in the infinite for this order parameter, I want to have an infinitely long string, so I kind of have to, right, go along that 1D line. But maybe one comment to make is, one thing I can really not imagine just being also a coincidence is we get at least part of these SNT matrices, like by getting different ground states and doing spatial rotation. Maybe this is a good way to say it. Here we really do a pi/3 rotation. So this is really violating this 1D-ness of the system. So here we're actually doing a system on a torus. And I do a spatial rotation, I overlap different ground states. And this is the theoretical prediction if you had a Z2 spin liquid. Basically, the point when I want to focus on, for example, all of these components being a half, right? And this is what we numerically get. So this is just as a function of sweeps. So these quantities converge to a half. I cannot imagine a 1D explanation for this, but okay. I'm not sure if it's 100%.
Yeah, that's pretty convincing. Maybe if I can ask one other question. So you mentioned about using this as like a topological memory. Have you thought about like the potential for manipulating like the corner defects to actually do some kind of gates on this?
Corner defects, so the kind of defects between different boundaries, or what?
Yeah, like if you had this surface code, then if you wanted to actually implement gates, you'd have to move these corners around or introduce defects some other way. Have you thought about doing that? Yeah,
we haven't thought like at this still early days. One thing definitely, even just initialize the qubit, you would want to do something like that. You would maybe try, you would start in all M condensed boundaries and like nucleate an E condensed boundary and slide it open. The next step indeed would be to think about gates, and then you would, I agree, this is the kind of game you might want to play. But I have not much to say at this point. Yeah, I agree, this is the direction.
Okay, thanks.
I have a closely related question actually. So have you thought about bulk defect? So you had a figure with the trap E in the bulk. Have you thought about maybe modify this figure a little bit to have something like a dislocation? And there may be a defect in the bulk, which, you know, the fusion rule is not appealing. You may have a topological qubit using that defect.
Right. It's a defect. So you don't just mean a hole, right? You want like a defect with.
Yeah, kind of maybe. So there, first there is a hole, and so the upper and lower the lattice. So yeah, we want to maybe shift the lattice slightly by maybe half of the lattice spacing for the half of the line. Maybe it depends on the lattice.
I see.
But
what so you would is it something, some bulk analog of, for example, this boundary junction having a Majorana mode effectively?
Yeah, it's a sort of similar, but I think that's something purely in the bulk.
Yeah, we haven't thought about that. That sounds
kind of similar. Yeah.
something like dislocation, right?
Yeah, that sounds
yeah,
great to think about, actually. Yeah.
Yeah, because like using anion, it's a quantum dimension is square root of 2. So if you have a few of them, you can still there's some non-trivial degeneracy.
Right.
And
Yeah,
it also modifies the topological entanglement. Maybe that something can be observed numerically.
Right. Yeah, that sounds good. I haven't thought about it yet, but I guess, so maybe you know the answer for the toric code. So if you're saying if it's a toric code and you have like a dangling leg in the middle of the bulk that's mismatched, it's something.
Yes. Oh, and by the way, there's a further effect on the string operator. So suppose there is a defect, then you can try to, so let's say there is a E particle and you braid it around and come back, it will become M. So it change E and M.
Yeah, that sounds, okay, that sounds amazing, yeah.
Yeah, I think it's a good time to end the talk. Yeah, I will stop recording.